we can really see, reconstruct the pre-impact stratigraphy. And so relating, starting from the diameter, from the rim to rim diameter, so from the final diameter of the we could even reconstruct the maximum depth of melting, which corresponds, as we can see here, to the minimum depth of origin of the central peak. So basically, we could understand depth of each layer. So how deep was each layer, with showing a certain spectral heterogeneity. Of course, we can't say, at least at the time of this study, we couldn't say what kind of mineralogy, as I mentioned before, what kind of mineralogy we were observing, but we are sure that we were observing some compositional heterogeneities, and we also could reconstruct at which depth each layer was located. And this is very important. So, I mean, this is what we should do when we analyze terrestrial bodies. We should reconstruct the geologic history, and we should also, of course, we should analyze the crustal properties. Mercury, this is, let's say, a local scale approach. But then I thought, okay, let's be more ambitious. Let's try to apply this this approach on a global scale. Let's try to as you see, the white circles are the craters I have been selecting. Fresh craters, complex craters, so with this central peak showing this central resurgence, so showing these materials from greater depths. And you see here that it was very complicated to do this kind of intersection, because more than 4 million spectra, so it's really a lot, and it's really demanding also in terms of data processing time, and also in terms of hardware capacity. So I defined basically for each of those 121 fresh impact craters a number of impact units. So we see in red the central peak material, and then we see in orange the crater floor material, and then so on, crater fresh eject at 1 radius distance from the rim of each crater, and then other 2 annuli at 5 and 10 radii distance from the rim of each crater respectively. This was made